Let us learn about the maximum power transfer theorem. It has two cases, that is maximum power transfer theorem for DC current and for AC currents. Now we learn about the maximum power transfer theorem for DC currents. The maximum power transferred for source to the load when the load resistance is equals to the source resistance, that is Rs is equals to RL, where Vs means voltage source and Rs means source resistance and RL means the load resistance. Then we calculate the power in the RL from the above circuit. P is equals to I square RL. From the circuit, we know that I is equals to Vs by Rs plus RL. Since V is equals to IR, that is I is equals to V by R, substitute the I value in above P is equals to I square RL equation. P is equals to Vs by Rs plus RL whole square into RL. The power delivered to the load is maximum when Rs is equals to RL. P maximum, that is maximum power, is equals to Vs by 2 RL whole square into RL. Maximum power is equals to Vs square by 4L square into RL, where RL is equals to Rs. That is, then the final maximum power equation is equals to Vs square by 4RL. Case 2. Maximum power transfer theorem for AC currents. It states that the maximum power is transferred from source to load when the load impedance is equals to the complex conjugate of source impedance, where Zs is equals to source impedance and Zl is equals to load impedance and Vs is equals to source voltage. In Zs is equals to Rs plus Jxs and Zl is equals to RL plus Jxl. In AC currents, maximum power is transferred to the Zl when Zl is equals to complex conjugate of Zs, where asterisk symbol represents the complex conjugate. For better understanding, we will solve a simple circuit. Find the maximum power delivered to the load resistance in the given circuit. For solving this network, we can use network theorems like Thevenin's theorem or Norton's theorem, etc. First, we have to remove the desired branch AB in this network. In this case, we are using Thevenin's theorem. That's why we have to remove the desired branch, that is AB, load resistor. In this network, we know that the voltage across the 1 kilo ohm resistor is 0. So then the modified circuit is like this. Now we calculate the Thevenin voltage by using node voltage analysis method. Apply KCL at the node VThevenin's minus 10 by 1 kilo ohm plus VThevenin's minus 0 by 1 kilo ohm, that is equals to 0. Then finally we get VThevenin's is equals to 5 volts, that is the Thevenin voltage is equals to 5 volts. Now we will see the impedance calculations, then the circuit will be. So in this circuit, the voltage source is replaced with a short circuit. Then the current direction will be through R2. Then it is divided into R1 and R3 resistors. So R1 and R3 are in parallel with series R2 resistance. Then the calculations of Thevenin is equals to R1 into R3 by R1 plus R3 plus R2. Then finally we get Thevenin is equals to 1.5 kilo ohms. Thevenin equivalent circuits. After impedance calculations, we have to substitute the values of Thevenin's voltage and Thevenin's impedance in the equivalent circuit will be modified like this. Here voltage source Vs is equals to 5 volts and the source impedance, that is R Thevenin, is equals to 1.5 kilo ohms and the load resistance. From the above circuit, RL absorbs the maximum power when RL is equals to Rs, that is RL is equals to 1.5 kilo ohms. In DC current, when the load resistance is equals to the source resistance, that is Rs is equals to RL, then the maximum power is attained by the load. Maximum power delivered to the load P max is equals to Vs square by 4RL. Substitute the Vs and RL values from the above solutions by using a calculator. P max is equals to 5 square by 4 into 1.5k. P max is equals to 25 by 6 into 10 power 3. Then the final maximum power delivered to the load is 4.167 into 10 power minus 3 watts. That is 4.167 milliwatts.